Begin with familiar sequences, arithmetic sequences where each term is found by adding a common difference. For example, a plus d, a plus 2d, a plus 3d, and so on. The rule is add d each time. Next, geometric sequences where each term is found by multiplying by a common ratio. For example, ar squared, a cubed, and so on. The rule is multiply by r each time. But now a new question. What if instead of adding or multiplying, we use a calculus rule? The rule is each previous term equals the derivative of the next term. This key insight forces exponential functions. We call this the differential series rule. In the first form, it says p sub n of x equals the derivative of p sub n plus 1 of x. That means the previous term equals the derivative of the next term. There is an equivalent form, p sub n plus 1 of x equals the integral of p sub n of x with the constant set to 0. That means the next term equals the integral of the previous one, ignoring constants. Here's how we apply it step by step. 1. Start with a seed function n of x. 2. Keep differentiating until you reach a constant, which we call p0. 3. Integrate upward to produce p1, p2, p3, and so on. And 4. Add all the terms explicitly to form a series. Example A, constant seed. Suppose the seed is a constant, n of x equals c. Step 1. Differentiate. p0 of x equals c. It is already constant. Step 2. Integrate upward with constant 0. p1 of x equals the integral of c, which is cx. p2 of x equals the integral of cx, which is c times x squared over 2. p3 of x equals c times x cubed over 6. p4 of x equals c times x to the fourth over 24. Step 3. Add the terms. S of x equals p0 plus p1 plus p2 plus p3, and so on. That is c plus cx plus c times x squared over 2 plus c times x cubed over 6, and so on. Step 4. State the result. This infinite series equals c times e to the x. Verification, the derivative of s equals s itself. Example B, monomial seed. Now let the seed be n of x equals x. Step 1. Differentiate until constant. The derivative of x is 1, so the base p0 equals 1. Step 2. Integrate upward with constant 0. p1 equals the integral of 1, which is x. Notice this matches the seed. p2 equals the integral of x, which is x squared over 2. p3 equals x cubed over 6. p4 equals x to the fourth over 24. Step 3, add the terms. S of x equals 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24, and so on. Step 4, the result. S of x equals e to the x. Verification, the seed x, which bottoms out at 1, generates e to the x. Now try a linear seed. N of x equals ax plus b. Step 1, differentiate to find the base. The derivative of ax plus b is a. The second derivative is 0, so the base is p0 equals a. Step 2, integrate upward with constant 0. p0 is a. p1 is ax plus b, which is exactly the seed level. p2 is a over 2 times x squared plus bx. p3 is a over 6 times x cubed plus b over 2 times x squared. p4 is a over 24 times x to the fourth plus b over 6 times x cubed. Step 3, add the terms together, then group them. The total result is a e to the x plus b e to the x, which is a plus b times e to the x. Example D, general polynomial. Now consider a general polynomial seed. P of x equals the sum from j equals 0 to n of c sub j times x to the power j. Step 1, differentiate until constant. The first derivative is the sum from j equals 1 to n of j times c sub j times x to the power j minus 1. The nth derivative equals n factorial times c sub n. The n plus first derivative equals 0. So the base is p0 equals n factorial c sub n. p1 equals n factorial c sub n times x. p2 equals n factorial c sub n over 2 times x squared, and so on, until pn minus 1 equals n factorial c sub n divided by n minus 1 factorial times x to the n minus 1, which simplifies to n c sub n x to the n minus 1. Then pn equals the sum from j equals 0 to n of c sub j x to the j, which matches the seed. Next, pn plus 1 equals the sum from j equals 0 to n of c sub j over j plus 1 times x to the j plus 1. Notice constants are chosen so that at level pn, the seed is recovered. Step 3, add terms horizontally and group coefficients. Step 4, combine everything. S of x equals the sum of c sub j all multiplied by e to the x. Example E, non-polynomial seeds. But what if the seed is not a polynomial? Case 1, sine of x, its derivative is cosine. The derivative of cosine is negative sine, then negative cosine, then back to sine. The derivatives just cycle, never reaching a constant. That means there is no finite base p0. Case 2, e to the x. Every derivative of e to the x is still e to the x. It never reaches a constant. If we try to treat p0 as e to the x, then all pk are also e to the x, and the series diverges, no finite accumulation. Case 3, other functions such as logarithm of x or trigonometric functions. Their derivatives never vanish, so again, no finite base p0. Only polynomial seeds work because they have finite chains of derivatives. Why is e to the x its own derivative? Because only polynomial seeds, when processed by the differential series rule, collapse into some constant times e to the x. The rule is differentiate until constant, integrate upward with constant 0, then sum the terms. Polynomials succeed, producing s of x equals the sum of coefficients times e to the x. Non-polynomials fail because their derivatives never reach a constant, so the series diverges or cycles. Thus, only functions of the form c e to the x are self-derivative. That is why e to the x is unique.